Hello, this is Mahendra Didia. This book on liquid formulation is a on-demand dynamic supplemental book that uses Qubit's video format. In this portion of the book, we continue to cover solution dosage form using an integrated approach for formulation development. This is a follow-up to Module 5 on pre-formulation. Pre-formulation information is used to select composition, that is excipients, and quantitative composition. This Module 6 on formulation and composition comprises of 3 related videos: solvent, cosolvent, and surfactant, separate submodule on auxiliary agents, and the formulation composition that contains several examples. Formulation development is a follow-up to pre-formulation. Storage conditions, degradation profiles, stability and robustness of formulation are all part of the development of formulations. It starts with pre-formulation, analytical and assay development, excipient screening, and dosage form. In this particular portion, we are looking at liquid and topical dosage forms. So formulation development includes laboratory studies as effect on bioavailability and manufacturing processes. Formulation and composition. Solution formulation, as discussed before in earlier modules, is a clear homogeneous liquid in which one or more solutes are dissolved in solvents or mixtures of solvent. It's a monophasic system. It contains solvents. In addition to that, it may contain cosolvent, surfactant, and auxiliary agent that are necessary to make formulation usable. Auxiliary agents range from pH, buffering agents, preservatives, preservation agents, rheologic modifying agents, organoleptic agents included in the formulation. So let's look at a simple diagram here. Solute is a substance that dissolves into solution, in this case shown as a salt cube. If we just add it to a solvent, shown here, this is not a solution at this stage. It is not evenly distributed. Once we mix it or energy is applied and it becomes homogeneous, we refer to that as a solution. In a processing, we use mixing. Solvent is an important component of the solution. Water is a common solvent used in many preparations, oral, ophthalmic, injectable solutions, common in pharmaceuticals. Chemical and physical attributes of water molecule make it very attractive solvent. It disrupts internal force that's holding the solute that's disturbed by water molecule with hydrogen bond formation. Many types of water are used in manufacture of pharmaceutical and cosmetic products. Purified water USP is used in oral medication, published in USP as well as by FDA. In cosmetic products, deionized water is commonly used. Ethanol is used as a solvent and a cosolvent. Ethanol is clear, colorless, and volatile liquid. It evaporates at moderately high temperature. It is completely miscible in water due to its strong hydrogen bonding. It also contains non-polar groups, CH3CH2, and non-polar molecule dissolved. It acts as a solvent or a cosolvent. Readers are requested to refer to submodule video 2.1 on physicochemical characterization, in which the solubilization by water and solubilization by nonpolar substances are discussed. Cosolvents. Solvents depending on the drug product and or cosmetic product. Glycerol or glycerin is cosolvent. It's miscible in water, alcohol, propylene glycol, and polyethylene glycol. It has a slightly sweet taste and it has a high density. Material that provides higher density, we would use glycerin with a sweet taste. Propylene glycol is also used as a cosolvent. It's clear, colorless, slightly sweet taste, and density of 1.04 grams per milliliter. It dissolves wide variety of solutes, corticosteroids, phenol, alkaloids, anesthetic, and also it has emollient and emulsifying properties, useful in cosmetic formulation. Polyethylene glycol, PEG 400, is commonly used as a cosolvent in pharmaceutical preparations. PEG mass range anywhere ranging from 200 to 8,000. Lower mass range products are liquid or at lower temperature, and therefore they are used as a cosolvent in pharmaceutical preparation. Clear, colorless, viscous liquid at room temperature. They can also be used as a surfactant to lower surface tension. Cosolvent with water is the hydroxyl groups. And we have groups as shown here that allows non-polar substances to dissolve. Cosolvent have miscibility in water and other solvents, as well as they are very good for non-polar substances. Silicone-based solvents and cosolvents are very common in cosmetic industry. Decamethyl cyclopentasiloxane, also called cyclopentasiloxane. It is approved in US for the use and is listed in USP. It's colorless, odorless, has a density of 1.02. It's insoluble in polar liquids. Solubility is low in water. It requires cosolvents such as anhydrous alcohol, mineral oil, dimethicone, and it is extensively used in skincare and hair care products because of its spreadability, and it can incorporate non-polar molecules. Dimethicone can be modified to increase its solubility by adding a phosphate group, and it's used in cosmetic, skincare, and hair care products. Surfactants. These are the molecules that contains both polar and non-polar groups. They reduce surface tension between water, solute, and air and allows water molecule to spread. So it acts as a wetting agent. Shown here, water will form a bead and it does not spread, has a very high surface tension. By adding surfactant, it lowers the surface tension between water and the substrate, and then water will spread. This would allow solute to hydrate and help in the solution of it. Surfactants are also used in micellar solubilization. Example of phenofibrate, which is insoluble in water, can be solubilized as shown here by using twin and sodium lauryl sulfate. It will form a micelle which is soluble in water. Example of solubility of two drugs in various surfactants are shown. Surfactants are STS, sodium dotacyl sulfate, CTAB, citramonium bromide, that's a cationic, and polysorbate twin AD structure, which is a non-ionic. Drugs are glyburide and glycoside. These drugs are not soluble. The solubilities are in microgram per ml, insoluble in water. However, when we add surfactants, solubility increases. Combination of STS and twin and combination of CTAB and twin increases solubility from 37 microgram to 14,000 microgram per ml. Solubility is affected by other solutes. Sodium chloride increases solubility initially, however, it's decreasing for the combination of STS 280 and CTAB and 280. Buffers can influence solubility. Solubility does not decrease, which is a good. That is, buffer will protect the molecule during stability. Glyburide, insoluble drug, and it does not increase when sodium chloride is added or buffer is added. It increases with surfactants, and 180 increases the solubility by 100-fold. In this case, STS and twin do not increase solubility. However, with the salt concentration, solubility increases quite a bit. So that's pretty good news, and one can use that.